Exactly. I tell you what I've been working on basically the last 4 years, and it's mainly the wavelength calibration of espresso. So why do we need good wavelength calibration? We all know. I don't have to explain you this slide. It's just I want to remark that here, if you really do RV studies, you're doing a differential measurement of different epochs. So you care about stability, and systematics cancel out as long as they are stable. But there are other very interesting science cases, and this one is the one I'm most excited about and was the second science driver for espresso. This is actually measuring the fine structure constant all across the universe. This is a sketch how it works. You observe a very distant light source, in this case a quasar, and you have some intervening gas cloud that imprints absorption lines. They're all from the same gas, but they're different transitions. And if you would assume that I could turn up and down the fine structure constant, it changes the energy levels of these atomic transitions, and you can compute by how much. And some of these transitions are very sensitive to it, and others are not. So you see some lines move, some don't, some move in the opposite direction. So if I take a spectrum of this and measure very accurately the wavelengths of these absorptions, I can tell what is the value of the fine structure constant at the time and place when this absorption happened. And this might be 10 giga-years in the past and far away. But of course, this sketch totally exaggerates the scale, a factor of 100,000 or so. So actually the movement of the shift of the lines that we want to measure is about 20 meters per second. And here we really need accuracy, because it's in principle a single shot experiment. You take one spectrum, you measure, and you need the wavelength calibration to actually be correct, not only stable, but correct to the 20 meter per second for the level we want to achieve with espresso. And there's another even more demanding science case already mentioned, the sandwich test. So observing the universe expand in real time. So you again look at distant objects, and the best case here are quasar spectra with a Lyman alpha forest that provides a lot of absorption lines. And where you see here the observing the year where you observe it ticks up, you see how the whole spectrum changes. And here, of course, I've exaggerated even more. The real shift here is only, depending on the redshift, a few centimeters per second per decade. So it is one of the science drivers for ELT Andes, but of course this is very ambitious. So I'm in the Andes team, and so in the last half a year, we first actually wrote down what we mean with precision, accuracy, and stability, and defined the requirements. And it's just for Andes, the accuracy is crazy numbers, 1 meter per second, and the stability in RV over the lifetime of the instrument is 1 centimeter per second. This is, of course, kind of crazy and about an order of magnitude more demanding than everything we have today. But there are still 10 years time, so let's start working. And one of the things I've done in the last years was analyzing the Fabry Perot wavelength solution of espresso. So 2 years ago, kind of there was the paper by Ryan Terrian showing this for HPF, and I said, yeah, let's repeat it. We have all the data with espresso, and I copied the analysis, but I did it just with thorium spectra, so no LFC involved here. We had 1,500 epochs over two and a half years, a lot of measurement points. And if I bin them together and do first kind of average in time and just get just the wavelength dependence that you see on the top, that's just the average spacing of the eta law as function of wavelengths, typical one. And to the right, this is just the achromatic drift, averaging over wavelengths, and it's quite good, a few centimeters per second per day. And kind of 2 years ago, we have expected that the residual of this, what you see in the center here, is 0, but it's not. And here over the 2.5 years, we actually see a drift of 20 meters per second. So this translates also to a couple of centimeters per second per day. So actually comparable to the achromatic drift. And it is not a particular pattern. If you look at this as function of wavelength, so comparing two epochs that are 2.5 years apart, we see some wiggly pattern here as function of wavelengths. And although the Fabry Pro is totally different from the HPF one, this, in my eyes, still looks qualitatively rather similar. And I think it's probably every FP is affected by this effect. But in the end, we want to check if this is really the FP. So I looked here at archival data of Tau Ceti to see if this effect is really there on sky. And what you see, it's 2 epochs, 3 years apart, similar time scale. What we see, and I computed the radial velocity for each spectral order, so we have it as function of wavelengths, and what we see is pretty much the inverse of the Fabry-Perot drift. So this is from the old data reduction system that did not take this into account. So what we have, the star is actually stable. Our Fabry-Perot drifts, the data reduction does not take this into account. So we basically copy in the inverse of the drift into our sine spectra. And this was enough to convince Christophe to take action. And over the last year, together with Danuta, they implemented a modeling of the chromatic drift in the DRS. And so this is now taken into account. And if I just show the same data on Tau Ceti with a new DRS, the chromatic drift is completely gone. So it's all nice now. So we know our Fabry-Perot drifts. It drifts dependent on the wavelengths, but so what? As long as we can model it, we're good. On the other hand, all the wavelength solution, wavelength information here in the end comes from the thorium lines. And although they carry us quite far, at some point their RV information is finite. So if we really want to do the sandwich test or so, we need laser frequency comms, and we have talked a lot about them. In principle, they're the ideal source because they have log to the SI second, super narrow lines, but in practice, they're quite challenging. And now for Espresso, the current status is that since November or so, the LFC works again, and we actually get a nice flat spectrum in flux, similar to the Fabry-Perot, but the flat one is the LFC. We have coverage from 430 nanometers all to the red end, but there are still some bugs. It's not reliable, and ESO does not yet offer the LFC officially to the community. Still, the data is in the archive, and one can do stuff with it. And this is kind of the analysis I did already in my 2021 paper. It's a comparison of the thorium-argon FP wavelength solution to the laser frequency comb solution. And this checks, of course, for accuracy, and in an ideal world, they would be fully consistent. But you see a lot of structure here, a lot of discrepancy on large scales, a global offset, but also on smaller scales. And what's for me, the particular annoying part here is, like in the blue, you see these hooks that go downwards, and this is modulated by the order structure of the instrument. And you also see we have four lines here for 2 fibers times 2 slices. We have a pupil slices, so 4 times we ask the same question, but we get different answers. And this is obviously a problem just with Espresso and not with the calibration sources. So where does it come from? The prime suspect was the line spread function, because here it's all assumed to be Gaussian, but it's not. And the laser frequency comp has fully unresolved lines, while the Fabry-Perot are marginally resolved, and this might do the difference. So in the last half a year or so, I spent quite some effort to measure the line spread function from LFC spectra. That's actually not so simple, and in the end, I adopted the approach by Toyoki Hirano. Thanks for writing that down in your paper from a couple of years ago. And you see here an LFC spectrum, and the step is, you need basically the line position, the line intensity. You need the background. We have quite a lot of diffuse background here, and the wavelength solution and the line spread function. So I first take the background, then I fit the lines with a Gaussian, but actually I know that intrinsically they're super narrow, I think 5 centimeters per second or so. And then I fit for the line spread function that convolved with these infinitely narrow lines produces the observed data. This is a Gaussian process deconvolution. I will write that down in the paper. I do it. It's kind of like the Hirano paper with some upgrades. And then of course comes a step, if I have established a line spread function, I have to refit all my data using this line spread function. And then also first the LFC and then also the sine spectrum finally. And I get really nice line spread functions. This is in chunks in one order. And you see it changes along the order. It's at the left, it's more Gaussian. On the right, it's pretty skewed and asymmetric. In another order, you can see that kind of towards the right here, the line spread function becomes kind of boxy. So it looks more like a top hat than a Gaussian. And I can do a lot of stuff with it. For instance, measuring the full width half max from the empirical models and plotting it as a function of detector positions with the blue detector on the top, the red detector on the bottom. And for columns indicate 2 fibers and 2 slices. And you see that the resolution actually changes quite a bit, but it's also not identical for all 4 fibers and slices. And what's even more telling is if you look at the skewness, here are very similar the first moment of the line spread function. And you see here that for slice B of the blue detector, you have a really strong gradient. And this corresponds to something like 30 meters per second. Now, if we go back to this plot, in particular in the blue, for slice B, we had this large deviation from slice A. So might this be actually what we're seeing here, the line spread function? And so that's the solution. Yes, if I repeat the full analysis with a proper line spread function model, fit the LFC, fit the FP, fit the thorium, and then compare it the wavelength solution, I actually get this. This looks way better. And in particular, in the blue part of the spectrum, all 4 traces are spot on. There's very little discrepancy. The offset and the structure might actually come from the thorium lines. The laboratory wavelengths might not be perfect. There might also be blends. But what's introduced by the spectrograph is basically 0. There's nothing in addition to this. On the red part, there's still work to do. So if you want to be accurate, you really have to take into account the line spread function. But this needs perfectly unresolved lines that tell you about the line spread function, so a laser frequency comb. And we know blue laser frequency combs are difficult. So I'm part of one project, it's called BlueVis, and it has the goal to explore technology to actually build a blue laser frequency comb that goes to the blue and near UV part. It's an interdisciplinary project funded for 4 years. It's from Geneva, from DESI in Hamburg, from CSEM, Neuchâtel, and EPFL in Lausanne. And we explore new technologies. So one is an electromodulated comb and a lithium niobate optical chip to do the wavelength conversion. And actually, the last 2 weeks, we were at Observatoire de Haute-Provence to test our setup on the SOFI spectrograph, and we actually produced blue light, but it's way too early to give you something quantitative. So I just want to summarize. Good wavelength calibration is important not only for exoplanet studies, but also for fundamental physics and cosmology. And what we aim for with Andes is at the moment a little bit insane because we have to improve by 1 order of magnitude about the current EPRV goal. But I hope we make it, but it needs strong efforts. And 2 examples, like for the Fabric Pro, yes, it drifts wavelengths dependently, but we can model and correct it by just using hollow cathode lamp spectra. And if you want accurate wavelength solution, you really have to model line spread function. And this might also be important because you say, as long as everything is stable, for stability, I don't care. But this discrepancy, this inaccuracy is stable in the observed frame of the telescope. But you have the barycentric motion of the Earth, therefore your line actually moves, and this kind of couples an inaccuracy into an instability. So this might be not relevant at the moment, but when we do the sandwich test or so, we probably have to take care of that even for pure RV experiment. Yeah, and blue laser frequency combs are challenging, but research is ongoing. So that's my status at the moment. Thank you. And I'm very sorry I can't be in Santa Barbara and meet you at the coffee break. So I'm on Slack, and if you have further questions, I put my email address here. Thank you.